Well, hello class. This video is going to help with 12.4 or 5.4, and we are skipping 12.3 in this textbook for business calculus. We're doing the definite integral, and I'm going to go ahead and share my screen so you can see what I have written down. So we're going to do the definite integral, and the difference is we've been doing what we call the indefinite integral, and that's like a formula. Now we're going to start our idea of the definite integral, which our answer is a number. All right, so the idea of this is we're going to be looking at what we call the area under the curve. Okay, so sometimes it's called the area under the curve, which is the idea. What that area under the curve can tell us is the probability of something, which you might have done in stats, where you did the area under the normal curve. Same idea, but the curve doesn't have to necessarily be the perfect bell shape. Okay, and then the average values of the function, or it could tell us the future value of the continuous income. I'm sure I'm missing some things. There's a lot of things that a definite integral can tell us. So the idea is I'm going to have some kind of shape, like this would be the shape of my function, and I want to find the area from one x to the next x. Typically it's in the positive section, but it could be between two functions as well. So basically the shaded area is what I'm looking for. What is that area? Okay, I can use rectangles and add those up, which is called Riemann's sums, or left sums, or right sums, or midpoint sums. They are sums. And we're going to use Riemann's sums to find that area under that curve. We're going to find other ways in the next section as well. So what is the idea? So we're going to use a rectangle. And what do I mean by that? Is if I have an increasing function, so here's my function, I'm going to use the idea of a left rectangle. What's a left rectangle? Well, I'm going from 1 to 5, so I'm going to start with the left first number here, and I'm going to go up and over and down and create a rectangle. Okay, then I'm going to go to the second number, up and over, third number, up and over, fourth number, up and over, and then I am done because I'm going from 1 to 5. So where I put these little dots are where we went up and over. Okay, and then we're going to find the area of each of these rectangles and add them up, which is where the word sums come from. So you're finding the area of each rectangle and adding them up. So what we call right here is the change in x. Okay, change in x goes from 1 to 2. That looks like this, triangle x, change in x, from 1 to 2. So it's just 1 on this one. So we would go 1 across. How would I find this number here? Rectangle's length times width. How would I find that number? Well, I would go across, and where I hit the function is how tall it is. So I can put the number 1 into the function, the equation of this graph, and I can find that width or that length, whatever way, I don't know, we want to call this our width and that's our length? Sure. So to find this value, this length up here, we would use the function. Okay, so change in x, change in y, kind of the idea there. Okay, so these are our left rectangles, and they are giving us an underestimate. So I was saying left rectangles are less than the area, the actual area, because we have these gaps here. So it's a little bit smaller. Over here, if on our increasing, if we did right triangles, we'd actually start with the second number. So we're going to take that second number, go up to the graph, over and down. Second, now then we go to the, well, it's the third number. So, but it's actually the second in our series because we're only going from 1 to 5. So then we go up and over and down, up, over, down, up, over, down. So we start with the second number. That's why I put dots on them. Start with the second number, draw your rectangle up, go over. That is a right rectangle because you started on the right of the first little space, right? So if you start on the left, the first number, then it's a left rectangle. If you start on the second number, it is a right rectangle. And I can start anywhere I want. This is from 1 to 5, 1 to 5. I could do 2 to 4. I could do 100 to 200. I could do 0 to 2. So it just depends. All right, this one we can tell is an overestimate. Okay, so when we add up all these areas of all 4 of those rectangles, it is going to be larger than the area. So in some cases, we take this left and we take this right, and we get these 2 numbers and we average them because one's over, one's less. Okay, but they're all going to the same thing. So whether I use a left, a right, average the left and right, which I don't think we do in this textbook, but you know, either way. Or we can do a Riemann sum, which you'll see, which is a little bit different, more of using the midpoint or a spot in between each section. So any of those are going to be a way to find the area under the curve. Okay, so another idea here is the smaller the rectangles, the better the approximation. Can you visualize the more I get in there, the closer I will actually be? I only did 4 because I'm lazy. I didn't want to draw that many. And you can also use a midpoint. You can average those left and rights. And we can use other formulas as well, which we'll see. Okay, so what if I have a decreasing function? So those two look a little bit different. I'm going to go quick on the decreasing. So if you need, you can pause and write these down if you would like. So these are a decreasing function. So our original function is going down. So when I create my left, I start with the first number, again, 1 to 5. First number up, over, down. Second number up, over, down. I can see that this is an overestimate. So it's the opposite of increasing. For the right ones, I start with my second number of 2. I go up, back, and down. Up, back, and down. And this is going to be our underestimate of the area. Okay? All right. So couple things. These are some like theorems and ideas here. I want to make sure you get this in your notes. It looks a little blurry. Let me click this button real fast. So what are error bounds? Error bounds is the function is greater than 0. It's either increasing or decreasing on from A to B. Okay? And it's saying to take B minus A into the function, that's our Y value, absolute value of that times B minus A over N. So where we're going from, N is going to represent the number of rectangles, okay? This is the error bound for the area between the graph of the x-axis, greater than 0, and from A to B by left or right. So this is error from the left or right sum. So you might want that. In another theorem that we have is if we're above 0, again, where y equals above is greater than 0, which is just that x-axis and above, but it's actually where y is greater than 0. And you're decreasing or increasing on some interval, the left and right sums both approach the same number as n goes to infinity. So basically, as I make more and more rectangles, n represents the number of rectangles, as I create more and more rectangles, well, it'll be in the same space, but more and more, I'm going to get going to the same number, which we've already said. But that is it said in a theorem. The more rectangles, the better you are. Okay. So here is an example that we're going to do. I was going to rewrite this out, but I think I'm just going to show you my work. I like to work them out on my own, but here is an example of a problem. And this one is, we're going to do the left and right with this one. And then our next example is going to be a Riemann sum, meaning it's not exactly left or right. Oh, wait, all right. What's my function? Oof, my function is 9 minus 0.25x squared. What am I going to do with that? Well, what I want to do is I'm going to go over here, open a new tab and bring it over. And I'm going to say, what does this look like, Mr. Desmos? Desmos.com. I used to have that programmed in, but my computer crashed today. And I'm recording your videos for the second time. Yay! 9 minus 0.25 x to the second power. That's what my graph looks like. And this one says from 2 to 5. So I can see that we're crossing up here at about 9, or exactly at 9. We're crossing here at 6. And then we are only looking from 2 to 5. So we can see kind of what that graph looks like. So I'm going to use Desmos to get an idea of what my curve looks like. Okay, so when I go to draw this on my own, okay, I already added the triangles. That's why I was going to draw it myself by hand, but it's fine. So we were at 9, we were at 6. We just did an estimate. Draw your pictures. I swear it'll help. Then we were told n is equal to 6 up here. So what that is going to tell us is we're going to go from 2 to 5, but we want to break that up into 6 pieces. And that will give us what we call our change in x, or this distance right here. So my change in x is equal to, I'm going from 5 to 2, so 5 minus 2 divided by the number of rectangles are in. And I could actually say this as b minus a over n. That's how it would look in the formula sense for that change in x. And that's going to tell me 1/2. You might have been able to figure that out on your own. I have 3 spaces here. 1, 2, 3, and I want 6 rectangles. So I would go by halves. All right, so if I was to do my left, I would start with the 2, go up, hit the graph, go over and down. If I was going to start with the right rectangle, I would go to the second number, which is 2.5, go up, over, and down. So these lower ones represent the right, how the right would look, and then the left is the upper ones. All right, so change in x. Well, what the heck am I going to do now? All right, well, the whole idea of these is, I wrote it out kind of ugly, but that's okay. The whole idea is you have your change in x, this distance here, times wherever the function is at that value. So for my left sum, I want to start with 2 because my left goes up and over, so that distance is wherever the function is at 2. So I'm going to take the number 2 and put it into my function. Okay, and then I'm going to times it by the change in x. So this is just writing out my formula. The second part is going to be the actual calculations. Then we're going to add it to the second triangle. How many triangles should we have? 6, because n is 6. Okay, so our second triangle is at 2.5 for a function. So we're at 2.5 up and over, and then we still have that same change in x. Okay. The third one is going to be 3 up and over times that change in x. Oops, there we go. Times that change in x. Plus the fourth one is going to be 3.5 up and over times the change in x. So I have 1, 2, 3, 4, and then plus, here's the next one. 4 is my next number. So 3.5, 4 up and over, and then I went to 4.5. 4.5 up and over. So you will be 1 number less than the ending point when you do your left. So left starts with the first number, ends 1 in whatever your change of x is across. Okay, so write this out. Do not be lazy or you're going to confuse yourself. Then from here, what I'm going to do, and I just show the numbers, I'm going to take 2 and put it into this function. So I'm going to get out my calculator. I'm going to say, okay, what is 9 minus 0.25 times 2 was our first number, squared. That's going to give me 8. Okay, so here's where this 8 came from. I put this 2 into the function given. That gave me 8. What was my change in x? 1/2, right? We got 1/2 right here. Whoop-oo, change in x. So 8 times 1/2, and then I had to calculate out the next one, the next one, the next one. So there should be 1, 2, 3, right? Aren't I creating 6 triangles? Did I not lose it? 1, 2, 3, 4, 5, 6. Yeah. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I feel like I'm missing one on there. Did I not write one of them down? Either way. Okay. I missed this one. 1, 2, 3, 4, 5, 6. Okay. I do have them all. Ooh, I'm losing my mind. So then I just put in each of these functions and times by the 1/2, add that all up. That's why it's a sum. It takes a long time. You're adding up these things for a while. So I get that the left sum is headed to 18-ish, 18.5. Okay. How would I do the right sum? Well, I have to start with the second number, go up and over. So when I write out the right sum, I would start with 2.5, but I end with 5, the end, instead of 4.5. So I start one more over, and then I'm still timesing each of them by the change in x. So this is the area of the first rectangle, second, and so forth. Then I'm going to put each of these values into the function. Well, shoot, you already put in some of them. Should be pretty easy. Then if you're doing both left and right, I think some of them make you do that. Then I'm going to add that up, and I got 15.91. So that's telling me the area is about 15.91. So somewhere between 18 and 15, because one's over, one's under, is our area under that curve. Woof. So was this hard math? No. You're got to figure out what numbers to put into your function and times them by your change in x for each one. You're not going to have 20 rectangles. It's going to be like 5, 6, very minimal, and then add them all up. Hopefully 2. I think there are some that are really little. What if I wanted the error? How far off am I? I would put in the error is going to be less than or equal to. I put in these the A and B, subtract them, absolute value, and then the A and B divided by the 6. So if I calculate that out, I get 2.625. So the error is less than 2.625, excuse me. So our error is less than 2.6. So our error is not too far off for the left and right. Woof. Okay. All right. Riemann sum. We also have the midpoints. Let's see, where is that one more example? I'm going to do one more and then a little bit of an idea from a different theorem. Okay, let's see if you can see this through my little sheet here. Sure can. All right, so Riemann sum S4. What does that mean? It means sums with four different rectangles. For the function, here's our function, partition from 0 to 12 into 4 subintervals of equal length, and that are each subinterval from this one to this one, let CK, blah, blah, blah. Oh, you just lost me. What in the world is this asking me to do? Okay, so our first idea is we're going from 0 to 12, and we only want 4 subintervals. S sub 4 also represents, I want to do a Riemann sum with 4 rectangles. So good, we only have 4. So if I divide 0, I didn't actually write it out, but that's okay. So 12 minus 0 divided by 4 is going to be 3. That's going to be my change in x, right? Because I have 12 numbers, 0 to 12, and I divide them each in 4, or I divide it by 4, so each one has 3. Okay? So x sub 1, 0, our starting spot, 0. It's a little bit weird, but 0 is our starting, is at 0. Okay, x sub 1 is at 0. Why? Because it says, why? Because it's at 0. It starts at 0. Then you add 3, add 6, add 9, or add 3, add 3, add 3, add 3. Whoop. I feel like I didn't say that right, but basically you still find your change in x, okay, which is 12 minus 0 divided by 4, and then you're just going to list, those would be the numbers on your rectangle on the bottom, okay? Now I want to use this crazy information that they gave me to find my CK values. Well, what does that mean? It means I am going to take K minus 1. I'm going to go with, basically, I'm going to start with the 0, K0. That's what that's telling me. Start with the first one. It's like a left sum. You want to start with that first number. Okay, so K minus 1, and I want to go to K. Okay, I want to go on, and what am I finding here? Instead of that left number, I want to use CK numbers. I don't want to use the left. I don't want to use the right. I want to use something in the middle. So what they're saying to do is to take 2 times the first spot and add the second one and divide it by 3. I don't know why, but that's what they want you to do. So in that little rectangle, we're going to do 2 times one side plus this one and divide it by 3 to get the middle. Kind of like a way to find that midpoint, but it's not the exact midpoint, or we would add them and divide by 2. Okay, so what are we going to do for this first K value? Well, K equals 1 for our first one. We would put in our 1 minus 1, which is 0, which means I'm going to start at that first spot. So K0 is the first spot. Okay, so I'm going to take 2 times 0 plus the second number, which is 3. And that then divided by 3, which gives me 1. Woo! Basically, I'm finding this number and I'm going to use 1 into my function. Okay, that's my first one. My second one, K, will be 2. So what do? 2 minus 1 is 1. So really, I'm starting with that second number now. Okay, so when K is 2, so I'm going to go 2 times x1 plus x2, then put those values in, divide by 3, and I get 4. Okay, next one. The third one is now going to start with the third number down, the 6, because it's going to be 2 times the x to the second plus x to the third divided by 3, blah, 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 which is 7. And then the last one will be the 4, which is going to be the 9. And then the x to the 4, which I didn't write up there, would be 12. Why didn't I write it up there? I'm going to take this out of my sleeve because I'm going to add my x to the 4. I don't know why I didn't write it. Okay, so x to the 4 here is going to be 12. Okay, so these values are kind of crazy. Now let's think about this just a little. I don't remember exactly what that function looked like. I don't think I drew it on my graph at all. So I'm going to steal it. So we are going from 0 to 12. So maybe I graphed it on the other side. No. Let me move that over and just show you on Desmos. That'll be quick. Bingo. Okay. And my face is in the way. All right. So we are going, here's our function. 61 minus 6 squared. And we want to go from 0 to 12. Okay. So some of our graph will be below and some will be above. But if I scroll in and I think about, I'm going from 0 to 12 here. So every third number, so 0 is our first x1, and then 3, and then 6, 9, and 12 are numbers that we would break it up into. And we would go up and over for the left. But instead of doing in this from 0 to 3, we're going to use this C value, which gives us the 1. Okay, so we're still between that 0 and 3, but we're not using 0, we're not using 3, we're using 1. And that's what that CK or these C values come from. They're a way to find, there's some kind of average. Then the next section we know is from 3 to 6, and we're going to use the number 4. See, the number 4. So it's 1 above, right? And then the next section is from 6 to 9, and we're going to use 7. So there you go. It's a little bit to the left. Who knows why? I mean, there could be actual mathematical reasons for a lot of these Riemann sums. Okay, so what do we do from there? What does these values mean? Well, these values that we came up with are our sums C values. We only have 4 on this one. So our sum to the n is going to equal the function at that value 1 times our change in x, plus the function at the value 4 times the change in x, plus the 7, and then so forth. So then we're going to use the 61 minus 6x squared, and we're going to put this first value of 1 into our function here. 1 squared times 6 is 6. So 61 minus 6 is 55. And 3 was our change in x. We went 3 across, and we will have negative numbers because they're below the x-axis, which we saw. Okay, so if something's below the x, it's going to have a negative answer. Above, we'll have positive. So then we're going to add these up, and this sum is going to a negative, which made sense because a lot more of that graph was under than above. And that's where I got a negative on this Riemann sum. Whoo! Crazy. Okay. One other slight idea that I'm going to give you. Okay, so of course I lost it. It's gone forever. We kind of talked about this. So a little bit. If I look at something like this, whoop, you can't see what I have. If you look at something like this on our graph, what is A? Negative area of A. It's negative. What's B? It's positive. So I could do stuff like, all right, so I could say your integral from A to B, so from A to B of f of x, and this is our notation from one to the next, which we aren't using very much yet. It'll come more in the next section a little, but we're saying from A to B like 1 to 5, or the last one was 0 to 12. Of the function dx, what would it equal if I'm going from A to B? It would be a negative A and a positive B. That's what the area under the curve would equal. So you have a couple problems like this, where you just are basically telling me some numbers. So I want to write out these properties. So please pause, write this notes out. But this first one is if I'm going from the same number to the same number, I'm going from A to A, 0 to 0, 2 to 2. What's the area under the curve? There is none. You didn't go any x. It's 0. 0 times anything is 0. Okay. If I'm going from A to B of f of x, from A to B of f of x, then if I want to go the opposite way, from B to A, it's going to be negative. I went the other way, B to A. It's going to be negative. Okay. Another thing that we can do on indefinite or definite is we can take a constant out. Okay, so if C is a constant, or K is a constant, excuse me, we like to use K in the definite and C in the indefinite. I don't know. So if K is a constant, you can take it out and you can calculate your very long Riemann sum or whatever right-left sum you have, and then times the K back in. Okay, so another thing, we can still break up functions. We can break them up if we need to. All right. Woo-hoo. So if I have something, oh, I had one more property. if I go from A to C of a function and you go A to B and then B to C, you could break that whole function up as well. Last property. Okay, so basically if A to C is the same as this one plus this one. So you can break it up that way as well. Here's my example, last one. I keep saying that like it's the last one. No, we're gonna be 20 more minutes. All right, so we wanna go from A to C here, and we're gonna do some different stuff. And we gave areas, right? So part A says from A to B, what is the value of this function? Well, A is negative, so we're going from A to B. We're just doing these ones. A is negative, so I would take negative A, so negative 2.3, plus B, which is positive 10, and that would give me 8.34. Okay. Second one, I want to go from A to C all the way across. Then I would take negative A plus B plus negative C, because these are both in the negative. And that you better give me 2.71 with the numbers that they gave us. Pause it. Try the next one, B to C, and see if you can get this solution here. Okay, B to C, it's negative. So you do the negative section in there. Okay. I do have another one. I could give you another example. I think I'll stop there because there's some videos from the program as well. All right. Okay. The sums are a big old pain in the bottom. So we have a whole another section that's going to be a shorter way. But you have to try them. All you're doing is coming up with which value, right, on your bottom for your change of x, where you're going, right, which numbers between each section, and then you're timesing it by where the function is for that y value, and then you add them all up. Woo! And then this idea at the bottom here, you'll do some that are just giving you the area and you add up. All right, done. I'm done with that. Hopefully that's helpful. Stop share.